Hi, everyone. Welcome to York University's Applied Algebra Seminar. So today we have Yibo Gao from MIT, Massachusetts Institute of Technology, and he'll be talking to us about the 1/3, 2/3 conjecture for Coxeter groups. Go ahead, Yibo.
Yeah, thank you very much, Aaron, for the introduction and invitation, and thank you all for coming. So I will be talking about the 1/3, 2/3 conjecture for Coxeter group. This is joint work with Christian Gates, and we are both students of Alex Posnikov. Before I begin, I just want to say that I am not an expert in the 1/3, 2/3 conjecture. And this talk is really about the perspective of generalizing this 1/3, 2/3 conjecture to Coxeter groups. And hopefully I can convince you that it really is a correct and cool generalization. So as for the agenda, we'll first introduce the 1/3, 2/3 conjecture, which is still wide open, by the way. For the background, we'll talk about weak order and convex sets so that we can generalize the setting to Coxeter groups. And as you can see in section 3, 4, and 5, we will talk about special cases where we are able to solve this conjecture, which are the fully commutative case, the generalized semi-orders, and a uniform lower bound for the balance constant for finite Weyl groups. And finally, we end with some examples. All right. Hopefully, everyone is familiar with this concept.
Quick question, Yibo. Have you been scrolling through slides, or are you still on the title screen?
Sorry, what?
Are you still on the title page, or are you on a different page? Because all we see is the title page.
This is still the title page?
Yeah.
Okay, this is very bad.
It's not moving so forward.
No, it happens sometimes. Oh. So that's why it's good to double check.
Yeah, okay.
There we go.
So now this is not the title page, right? But
yeah, now we're on linear extensions of posets.
Yeah, now it's moving.
Is it moving now? Okay.
Yeah.
All right. Yeah. So either way, this is the overview, which is not very important. So yeah, that's fine. Okay. All right. So a linear extension. So here P is a poset on n elements. A linear extension of a poset P is an order preserving bijection from this poset to the n element chain 1 to ... n. Just for a piece of notation, we let uppercase E of P denote the set of linear extensions of P, and lowercase e of P to be the number of linear extensions of P. So to introduce the 1/3, 2/3 conjecture, let's define another piece of notation. So for a pair of elements PQ in P, we will let delta PQ to be the fraction of linear extensions such that P appears before Q. So if P is less than Q in the partial order P, then obviously we have delta PQ equals 1 by definition of the linear extension. And similarly, if P is greater than Q, then we have delta being 0. And we also see delta PQ plus delta QP always equal 1. So the famous 1/3, 2/3 conjecture states that for any finite poset P that is not a total order, there exists a pair of elements PQ such that this delta PQ is between 1/3 and 2/3. So we see that if it is a total order, then all of the deltas will be 0s and 1.
Wait, can I ask really quickly, what is it for a total order?
It is, I'm just saying all the deltas are going to be 0s or 1s for a total order.
Thanks.
Yeah, so that is essentially a trivial case that we want to exclude. And so another way of saying this is that we can define the balance constant of the poset to be denoted B of P. So we take the maximum over all the pairs PQ in P, and we take the minimum of delta with 1 minus delta. So this is just saying that we are going to let this constant to be at most 1/2. Then this 1/3, 2/3 conjecture just says that for any finite poset P that is not a total order, the balance constant B of P is at least 1/3. Okay, any question? All right. So yeah, why 1/3? So if we look at this example here, this poset has 3 linear extensions: 1, 2, 3, 1, 3, 2, and 3, 1, 2, with the following delta that you can see. So basically, delta P1, P3 is 2/3. Delta P2, P3 is 1/3. So all of these deltas are going to be either 0 or 1 or 1/3 or 2/3. So in this case, we have B of P to be 1/3. And you can construct more examples by taking direct product or it's called direct sum and disjoint union of these poset to get other examples with equality case.
May I ask a question? Do you know, and for example, if you're like here, you have an example of a poset that is the disjoint union of 2 poset. Do you have some property of this constant with respect to disjoint union?
Oh, I don't think I know, but I don't think I don't think it behaves very well with disjoint union, this constant, but it should behave well with direct product or direct sum.
Okay, thank you.
Yeah, so if you think about if I have 2 chains, then this balance constant should be 1/2.
Yeah. Well, here you have 2 chain and it's 1/3.
Sorry, I mean 2 chains like of the same length. Yeah.
Yes.
Hey, that's a good question. Right, let's just go on. So it is non-trivial to even show that BP is uniformly bounded away from 0. So I'm going to list some results here. Cannon-Lineal showed this for 1/2E. Cannon-Sachs 3/11. Weyl, Felsner, and Trotter 5 minus square root 5/10. So all of these uses some techniques or like some tools regarding log concavity, like Bruminkowski or Alexandro-Fenchel inequality. All of these are in some sense geometric. There are also special cases where the full conjecture is known. So these are with 2 posets, semiorders, height 2 posets, series parallel posets. So the results on the lower half is going to be easier, and we are going to talk about some of the generalization. Right, so moving into the background, hopefully everyone is familiar with these, but let me say this anyways. A Coxeter group W, by definition, is generated by a set of so-called simple reflections S, such that, well, these are involutions, so SI squared equals the identity, and we also have SI, Sj to the power of Mij equals identity. So Mij here is allowed to take on values, positive integers to be at least 2, or it can be infinity. So when it's 2, it means that Si and Sj commute. And when it's infinity, it means that there's no relation between Si and Sj. So for the first half of the talk, we are going to talk about the setting for pretty much arbitrary Coxeter groups. And we'll be looking at finite Weyl group later on. Standard notation, let L of W denote the Coxeter length. And the left weak order is going to be the transitive closure of this covering relation W less than SW if the length of W plus 1 is the length of SW for some simple transposition S. Okay. Now let WS be a Coxeter system. So this means that W is the Coxeter group and S is the set of generators. The reflection is defined to be the conjugate of the simple reflections. Simple reflections also means S, the generator. The right inversion set of an element W is defined to be the set of reflections such that if you multiply W on the right by T, then the length decreases. And it is a really helpful proposition and really classical proposition that says that the left weak Bruchau order is characterized by the inclusion of the inversion set. And as a classical fact, the length of W is the size of the inversion set. Now let's define the convex sets in Coxeter groups. I'll let H be the Hasse diagram of the weak order. A subset C of the Coxeter group W is called convex if for any pairs of elements x, y in this set, any shortest length path between x and y remains in C. This is more of a graph theoretic definition of a convex set. An old proposition by Tietz says that any convex subset C of the Coxeter group W is of the form W sub A sub B, which is, by definition, the set of Coxeter group element W whose inversion set contains A and is contained in B. This is not very hard, and you can also just think about this as the definition of a convex set. And for our purposes, we can usually translate a convex set C by some Coxeter group element W, we'll just multiply it by W, to assume that this A here is the empty set. Or if you want, we can also assume B is all the reflections equivalently. Okay, so this is the definition of a convex set. And let's just look at an example here. The symmetric group Sn is a Coxeter group of rank n-1 generated by the simple transpositions I plus 1. The reflections, which are the conjugates, are all the transpositions ij. And we see that the reflection ij is an inversion of a permutation W if Wi is greater than Wj. So we can look at a convex set here. Can you see my mouse, by the way?
Yeah, we can.
Oh, okay, yeah. And so for example, here we have identity 1, 2, 3, 4, 1, 2, 4, 3, 2, 1, 3, 4 here, 2, 1, 4, 3, and 3, 1, 4, 2. So you have this square plus an edge thing. So this is a convex subgraph of the weak Bruchau order. And you can also write this convex set as W sub empty set sub this 1, 3, 2, 3, 2, 4, which means that it is the set of permutation whose inversion set is contained in 1, 3, 2, 3, 2, 4. All right, so why are we talking about convex set? For a poset P, any linear extension is really naturally in bijection with permutations. So here we are going to just naturally identify the set of linear extensions E of P to be a set of permutation. Very simple proposition says that the map from the poset to a set of permutations is in fact a bijection between labeled posets on n elements and convex sets of the symmetric group. And so when we are talking about this 1/3, 2/3 conjecture on poset, we are really talking about something about convex sets of the symmetric group. And so this is the example from last slide, essentially. So it is this is the n poset with 4 elements, and we see that the linear extensions 1, 2, 3, 4, 2, 1, 3, 4, 2, 1, 4, 3, 1, 2, 4, 3, and 2, 4, 1, 3 form a convex set, and this is what you just saw. Recall that we have the definition, which says that delta Pj, Pi is the fraction of the linear extensions where Pj appears before Pi. And another way of phrasing this is the set of permutation W in this convex set C sub P, where Ij is the inversion. Ij is an inversion of W. So this suggests the following natural definition. So if we have a convex set C in a Coxeter group W and T be any inversion, then we can define delta T to be the set of Coxeter group element W who contains T as one of its inversions. Similarly, the balance constant defined to be the max over the inversions T, and we take the mean of delta and 1 minus delta, so that it's almost a half. So remarkably, what I think is the most amazing thing about this is that the natural generalization of the 1/3, 2/3 conjecture still seems to hold for any finite Coxeter group. So this is the main conjecture that we have, which says that let C be a convex set in a finite Coxeter group with it has at least 2 elements, because when it has only 1 element, you always have B of C equals 0, and this is the same as saying my poset is a chain. Then we conjecture in this case that the balance constant is at least 1/3.
So in this generalization, do you cover exactly all possible poset? For any poset, there is a convex set?
Yeah, so that would be the type A case.
Yes.
The type A case will correspond exactly to
any kind of poset.
Any kind of poset.
Okay, thank you.
Yeah, that's a very good question. Yeah, so this is strictly a strict generalization of the poset. So one may argue that, well, any finite Coxeter group has some kind of type A2, well, or almost all of them have some kind of type A2 parabolic subgroup. So maybe this 1/3 just comes from this parabolic subgroup of type A2. But this is actually not the case. So there are new equality cases in every type that is not coming from type A. So I think this is a very surprising fact, and I will be showing those equality cases. So another way of thinking about this, when you are looking at finite Coxeter groups, yeah, so here we are really talking about the finite Coxeter group, so the size of the group is finite. Convex sets in the finite Coxeter groups are exactly the convex sets of regions in the corresponding Coxeter arrangement. So that's a much easier way of thinking about this problem here. And the conjecture just says that there's a hyperplane that cuts the convex sets into roughly equal parts. Roughly equal just means both parts will have at least 1/3 of the regions. So as we can see in 2 dimensions, this is pretty obvious. You have a bunch of regions; they must be consecutive, and you definitely can find some hyperplane that cuts it into roughly equal parts. So the extreme case is that you have 3 consecutive regions and you cut it into 1 and 2. All right. So now we are moving into the special cases. The first special case is the width 2 poset. But we will be introducing fully commutative elements in Weyl group, which corresponds to width 2 poset, essentially. So elements W of the Coxeter group is fully commutative if no reduced word of W contains a consecutive substring Si, Sj, Si alternating with M sub ij of them. All right, so this is just saying that if we have such a substring, then we can switch this Si, Sj, Si to Sj, Si, Sj, and so on. So it's like in type A, you have S1, S2, S1, and you can change it to S2, S1, S2. Yeah, so for example, in the symmetric group on 4 elements, S2, S1, S3, S2 is not, it is fully commutative because all the moves that you can do to this guy is you can swap S1 and S3 to do a commutation move. And you can never do something like S2, S1, S2, or S2, S3, S2. But this guy, S2, S1, S2, S3 is not fully commutative because we can apply a Coxeter move at S2, S1, S2 and change it to S1, S2, S1.
So little question about fully commutative.
Oh, Alex. Oh.
Is it possible that you may not be able to apply the Coxeter move immediately, but after you apply some commutation moves, then you will be able to apply the Coxeter move?
Oh, I mean, that's not fully commutative because it says a no reduced word of that.
Ah, no reduce. Yeah. Okay, just one.
Very good question.
Yeah.
Yeah, a very old proposition says a permutation W is fully commutative if and only if it avoids 3 to 1, so in the most standard sense of pattern avoidance. And correspondingly, on the poset side, we say that a poset has width k if its longest anti-chain has size k. And as we have seen under this bijection between naturally labeled posets and convex sets in the symmetric group, which two posets P corresponds exactly to the convex sets that's of the form, which is a lower order ideal below the fully commutative elements, an interval from the identity to W. So this is not very hard to see. So for example, when W avoids, when W contains, let's say it contains 3 to 1, then on the poset side, it's like you already have an anti-chain of size 3, which is like basically corresponds to this 3 to 1. So the 1/3, 2/3 conjecture is known for which two poset, and we are going to strengthen this result to other Coxeter group. This is the main theorem of the section, which says that let W be a fully commutative element in any Coxeter group, whose Coxeter diagram is acyclic, which is a very important condition here. Then the balance constant of the interval from the identity to W is at least 1/3. So in particular, this theorem applies to all finite Coxeter groups because all the finite Coxeter groups will have an acyclic thinking diagram. So I have an example here, which is actually a non-example. So in the affine Weyl group A3, whose thinking diagram is shown here, it is cyclic, not acyclic. So the theorem shouldn't apply, and this is really a common example. We take W to be S1, S3, S0, S2, and this is fully commutative. And actually, the balance constant for this interval is 2/7, which is in fact smaller than 1/3. And we'll actually come back to this example later.
Oh, just to clarify, in the previous theorem, the Coxeter diagram means the same thing as Dynkin diagram?
Yeah.
Ah, okay.
Yeah. Right, so yeah, I won't be talking about any of the proofs, but I'm just going to talk about some of the techniques or some of the tools that we use. So it uses the theory of heaps. So let S be a reduced word of W. And this heap poset H sub S, which depends on the reduced word, is the partial order on L elements. So it is the partial order on these I1, I2 dot ILs. And it is defined to be, so J is less than K in this heap poset if I sub J appears before S sub K and that they don't commute. Well, either way, this is some poset that's associated to a reduced word of an element. In the case where W is fully commutative, we can see that the heap poset does not depend on the choice of a reduced word. So we can then write the heap poset as H sub W. Yeah, a proposition by Stanbridge says that when W is fully commutative, then the lower order ideal below W in the weak Bruhat order is in fact isomorphic to the lattice of order ideal of this heap poset. These are not very hard propositions. You just get a correct understanding, and they just turn out to be true. So now we transfer a problem back to poset. but this is another setting of the poset. So very naturally, we can have this following definition. So Q is a poset in general, so a general poset. And we let J of Q to be the lattice of order ideals of Q. So we can define this new delta to be the fraction of the order ideals that contain X. And so this is just a fraction of the order ideal that contains X. And we can then define this new B of Q to be a very similar formula. So it's the max over all X in Q. And we take the mean of delta and 1 minus delta to make sure it's at most 1/2. And then for the fully commutative W, we have the balance constant for this convex set to be equal to this new B of the heap poset H sub W. All right, so let's look back for this non-example. If we consider this following poset Q, which is now the heap poset for the same W's as 1, S3, S0, S2 in the alpha and Weyl group, then this thing is the heap poset. It's not hard to count that there are 7 order ideals. You can convince yourself that. And for example, I mean, we can just count right now. 0 is all symmetric. So 0 is in 2 of the order ideals, right? Because if 0 is in the order ideal, then 1 and 3 must be in the order ideal. So you only have a choice for 2. So in this case, 0 is in 2 of the order ideals. Similarly, 2 is in 2 of the order ideals, 1 is in 5 of the order ideals, 3 is in 5 of the order ideals. And with this definition of B of Q, you have that it is 2 over 7, it's less than 1/3. So this is basically as far as I will go for the proof techniques. But I just want to say that this is my favorite proof of this presentation, just because it's in some sense, I mean, it's completely type uniform and really shows you that acyclic thinking diagram is what you want to look for. So yeah, I have mentioned that there are new equality cases coming from not the type A part of a finite Weyl group. So let me just show you some more examples. So the first one here is the type A thing. So on the poset side, this element S1, S2 corresponds to the poset that is a 2 chain and a 1 element. And that's
can I ask a question about the previous slide? So you said you had this new B of Q, and here's a non-example, so it's not always bounded by 1/3.
Yeah.
So is there some class of posets Q, then it's bounded by 1/3?
Oh, we don't know.
Okay, so you don't, so at least particular order ideals of
yeah, we don't look at this thing that much.
I see. So
but it happens to work for the heap poset of the fully commutative elements.
There's like no bigger class of posets, then we still have this bound.
Yeah, I mean, it is a very interesting concept to look at for posets, I believe, and it has context here. All right, so yeah, so the first line here, the type A2 is really the one where one corresponds to poset is the classical example of what you achieve for 1/3. If we look at the heap poset side, we see that this guy has 3 order ideals, right? So you have the empty one, you have the order ideal that contains 1 element, and you have the order ideal that contains 3 elements. And the lower guy is in 2 of the order ideals, the top guy is in 1 of the order ideals, so you get 1/3 by looking at this heap poset. Hopefully, yeah, that makes sense. And for type D4 and D3, we have these 2 more examples that kind of look similar, and the heap poset is the same. So this guy, for example, has 6 order ideals, and the lower guy are in 4 of them, and the middle guy are in 2 of them. So you still get 1/3. And in type E6, there's an even more complicated example here. And I think it has 15 order ideals, and this lower guy is in 10 of them, and this guy is in 5 of them. And you'll get 1/3. It's very surprising that you get genuinely different examples than in type A. Yeah, okay, so now we are moving into the next special case. And in fact, for the rest of the talk, we'll be mostly talking about finite Weyl groups. So semiorders. A poset P is called a semiorder or a unit interval order if there exists a function on this poset such that P is less than Q if and only if the value between them is at least 1. So it's called unit interval because it's like you can put your elements on a number line such that you say one element is greater than another if their distance, or like if one is at least 1 ahead of the other. So there's this theorem by Weyl saying that if P is a semi-order which is not a chain, then the balance constant is at least 1/3. This is not hard. And we'll be generalizing this result to finite Weyl groups. And for that, we need some good old definition of root systems and Weyl groups. So here I have the axiomatic definition of a root system. Hopefully everyone is familiar with this. But if this is the first time that you see this definition, a root system is essentially a finite set of vectors in my ambient space E, which are very, very, very symmetric, as you can see here. And for each root alpha, there is this sigma alpha, which is the reflection across this root. Some facts: let phi be a root system, the Weyl group is generated by the reflections across the roots. It is a special case of a Coxeter group. We can partition a root system phi into positive parts and negative parts. And for such a partition, there's a unique choice of simple roots, delta, which is the basis of our ambient vector space, such that each positive root can be written uniquely as an integral linear combination of the simple roots. So delta just means simple roots. There's a partial order on phi plus called the root poset, and this is given by alpha less than or equal to beta if beta minus alpha is a non-negative linear combination of the simple roots. I'm going to give an example.
I guess we should say like each positive root can be written as a positive combination.
Oh, I forgot. Yeah. I forgot to put poset there. Yeah, exactly. Each poset root can be written as a unique positive integral linear combination of the simple roots. And yeah, so in the root posets, the minimal elements are the simple roots, and there's a unique maximum, which is called the highest root. Right, so here's the root poset of type A4, symmetric group of 5 elements. Right, so all the roots look like ER minus EJ, and the highest root is E1 minus E5, and the E1 minus E2, E2 minus E3 are the simple roots. Okay, so recall that the convex set will have the form W sub A sub B, and this is the set of Coxeter group elements whose inversion set contains A and is contained in B. So our definition of a generalized semi-order is going to be a convex set C of the form W sub B, such that B is an order ideal of the root poset phi plus. So B means that so here B means the set of roots that we are going to allow for the elements to have their inversions. Right, so why this definition though? Let's see why this recovers the definition of semi-order in type A. So yeah, so just recall that the semi-order on P is defined by P less than Q if their difference from some linear function is at least 1. And let's say P is naturally ordered. So FPs are increasing here. Then the set of root ER minus EJ, where I is less than J, and Fj minus Fi is less than or equal to 1. So this is in fact an order ideal of the root poset. This is not very hard to see. And vice versa. So given a root poset, given an order ideal in the root poset, you can find such F. Okay, so this is our definition. essentially you allow an order ideal set of roots to be your inversion. Oh, and by the way, just one fact that I just learned, which is completely not related. So let's say I have an order ideal of a root posets. Then if I take the hyperplanes corresponding to these roots, then this hyperplane arrangement is free and is characteristic polynomial factors into linear factors. I just learned this fact very recently, and it sounds very, very cool. It's completely not related. Sorry about the digression. So our main theorem of this section says that let C be a non-singleton generalized semi-order. So non-singleton is always there to mean that we don't have B of C to be 0. So if C is a non-singleton generalized semi-order, then the balance constant is at least 1/3. And this theorem relies on the following purely root theoretic facts. It's not very hard to go from this lemma to the theorem. So this lemma says that if we have J, which is a non-empty order ideal, then there exists a simple root alpha in J such that we cannot find two distinct betas where if you reflect beta across alpha, you get something that's still positive, but it's not in J. Right, so this looks like a really simple fact, but we are not able to prove this in a type uniform way. So our proof is really, really bad. So it is very technical. It's the most technical part of this project, and it is type dependent, which is really disappointing, I think, because this fact looks very simple. So if you are able to figure this out, please let me know. All right.
So now the question about this theorem. So you said for posets, this there is no obvious relation between then you take unions of two posets, right? So you don't. So suppose you prove this conjecture for poset P and poset Q. If you take the union, then it's kind of not obviously true. Is that the case?
Yeah. I think some operations are good, some operations are bad, but I have to remember.
So I'm wondering if this theorem is true that for any, because here I think you need to assume that Dynkin diagram is connected. Look at this maximum.
I know that the conjecture behaves well when you take different parts of the Dynkin diagrams and put them together.
So it's kind of taking two the joint union of two Dynkin diagrams. I guess it's something like taking unions of posets.
No, it's not poset anymore because poset is irreducible already because it's type A.
So it's not union of posets, but it's some other operation on this.
I don't know if you can even talk about poset in that way when you take union of Dynkin diagram.
But just to clarify, you prove this theorem for any Dynkin diagram not necessarily connected.
That's right. Yeah.
Because to have the highest root, the Dynkin diagram should be connected.
So, yeah.
So this, like in general, this poset doesn't have a unique maximal element.
Yeah. So yeah.
So
you're right. Yeah. But here, this generalized setting of the 1/3, 2/3 conjecture behaves well under disjoint unions of the Dynkin diagrams.
And it's okay.
Yeah. That's a very good question. Yeah. The proof. Yeah. When I say proof is very bad, we check each irreducible part, put them together. Yeah. So recall that in the poset setting, it is non-trivial that these guys are bounded away from 0. The main theorem of this section. So we have. So let W be a finite crystallographic Weyl group of rank R with highest root C and the fundamental co-weights. And we define the following parameters. So what they are is really not important. Please don't look at them. Well, M0, so basically what are M0 and M1? So they are, when you write C as a combination, as a linear combination of the simple root, what are the smallest and largest coefficient? And M is just something. But what's a little bit more interesting is that these guys are constant in each type. So they are the same in, for example, type B5 and type B6. And the main theorem that we have in this section is that if we let C to be a non-singleton convex set in W, then the balance constant is at least 1 over 2 times e to the power of m times m1. And it is at least 1 over, it is at least this number, which is strictly greater than 0. So this number is really, really small, so this may not be very impressive. But here I listed these actually what these numbers are for each type. So in type A, we recover the original results by Cannon linear of this constant being 1 over 2e, so this is not very small. And in type BCD, we get, well, in type BC, we can actually also get 1 over 2e with some twist of arguments I will talk about. In type D, it's also not too bad. And the rest is the exceptional types. It's the worst in type E7, where this number is almost like a 20% or 30% of the whole Weyl group. So this is not so exciting there. But what's interesting is that it's sort of constant in each of the infinite families.
So why do you have fractional exponents like 10.5?
Well, it's just what's come up in the argument.
Okay, because like in the theorem, it's like m times m1. It's
this m can be.
Oh, m is fractional. I see.
Yeah. All right, so I will be talking about some of the proof ideas. So to do that, we need some convex geometry. So let W be a finite crystallographic Weyl group, and the fundamental alcove is defined to be, well, denoted Q sub the identity, and it is a simplex and is bounded by the linear hyperplane perpendicular to the simple root alpha, and also we take the affine hyperplane perpendicular to the highest root C, and which is bounded by 1. So this is the fundamental alcove. It's in the fundamental region of the Coxeter arrangement. And for each W in the Weyl group, the corresponding alcove is just defined to be a translate of the fundamental alcove. And as you may have guessed, we define the generalized order polytope to be the union of the Q sub W's, the union of these simplexes where C is a convex set. Yeah, so this is alcove polytope. Yeah, okay, so these are some examples. So on the left-hand side, we have type A2. So you have these two regions, and they form a polytope. And on the right-hand side, we have type B2, and you also have polytopes that look like this. And so why they're called generalized order polytope? Because they generalize the order polytope. When you are in type A, you recover order polytope, maybe with some linear transformation. Yeah, so these are special cases of alcoved polytope defined by Thomas and Alex. So we are going to use the geometric approach. For reflection T, we'll let H sub T be the corresponding hyperplane. And the hyperplane H sub T cuts the order polytope into two parts, the positive part and the negative parts. And the goal is to show that there exists some T where both of them will have non-trivial volume, basically. So the main lemma, well, one of the main lemma says that let C be a convex set of Weyl group of rank R, and let OC be the centroid of the order polytope. Then there exists a T such that you have this inner product to be small. So M is what I defined in the previous slides, where you can think about this M as a constant, but R is something that will grow. So this is the rank of the Weyl group. So in other words, there's a hyperplane H sub T that is close to the centroid. So this should really make sense. So you want to find a hyperplane that's close to the centroid so that it can cut your polytope into two roughly equal pieces. But this is not the end of the story, because even if you have a hyperplane that is really close to the centroid, it is possible that So for example, here, I don't think I've done a good job indicating what I'm going to show in this picture. But the lower half can still have a lot of volume if it's really close to this hyperplane. And the top half can have very small volume if it's like relatively further up. So it's still not so clear, and we need one more condition to finish the proof. So this proposition says that if Q is a full-dimensional compact convex body with centroid C sub Q, and we let n be a constant, such that, so this first condition says that the centroid is close to the hyperplane defined by V. And the rest of these two, so these two conditions says that, so this two conditions says that there is an X that is relatively on one side of this hyperplane H of V, and there's another point X which is like further from the hyperplane V on the other side. So basically, this says that this hyperplane is relatively in the middle of your convex body, such that you have some distance towards both ends of the boundary. And as long as we have these conditions, we can show that the volume is bounded below. Okay, so either way, this is some sort of argument. Our proof generalizes the original argument by Canalino, which uses the Brum-Minkowski. And Brum-Minkowski says that so this Q sub V sub lambda is the section where you use the hyperplane perpendicular to V as level lambda to cut your convex body. So you do these slices, and you take the volume of these slices. And if you take these volumes to the correct power, then this function is going to be concave. There's always some sort of log concavity things going on in all of the proof of a generalized lower bound for the balanced constant, and we are not an exception. And so the proof of the previous proposition is done by explicitly construct a convex body Q that minimizes this fraction, which is a double cone. And I think this is already a little bit too much of details that I want to go in. But this is basically the idea of how the proof of a uniform lower bound works. Yeah, so there's a little twist in type Bn that lets us get a little bit a better bound. So we can get 1/2 instead of 1/2e squared with the previous definition, and this is how we do it. So we define another order polytope. So here we define the alcoves Q sub the identity sub eta to be basically a similar thing, except this affine hyperplane you take is perpendicular to eta, where eta is the highest short root now instead of the highest root. So one may think that, of course, the short root order polytope is defined correspondingly by the union of these simplexes. So one may think that, well, why are you doing this? Why don't you just have any vector here? Like you have the hyperplane arrangement, which is central. You just have any hyperplane that cuts your fundamental alcove, and then you just translate it and you take the union. And the reason is that if you are not choosing this vector carefully in general, even if you have a convex set, you put them together, you are not going to get a polytope. It really works, I think, for very restrictive choice of things that you can put here. So one choice is the Cassie, the highest root, or you can put the highest short. Yeah, so just give you a sense of what type Bn root system is. So this is a standard realization. And by the way, our proof doesn't depend on any realization. So the roots in type Bn are of the form EI minus EJs, EI plus EJs, minus EI minus EJs, together with the coordinate vectors plus minus EIs. A possible choice of simple roots is all the EI minus EJs, sorry, all the EI minus EI plus ones together with EN in the end. And the highest root could see, well, it's also a long root, it's E1 plus E2. So long means that its length is long, its length is square root 2. And the highest short root is eta, which is E1. So the length is only 1. But either way, you have two versions of the generalized order polytope here in type B. And you run the same argument again, and you get a better bound. Okay, so finally, I'm going to talk about some examples. So let's recall that this balance constant is bounded from below for finite Weyl group. So one may wonder whether this is true for arbitrary Coxeter group. And the answer is that there's no universal bound, and the example can be very simple. So if we take Wn to be the Coxeter group whose thinking diagram is a complete graph, it has n generators, and basically none of the generator commute. Let me take the following convex set. Just take, so as a set, it just has identity and all the simple generators. And you can see that in this case, the balance constant is 1 over n plus 1. And it's certainly not bounded from below. So just one more example. In the original 1/3, 2/3 conjecture for posets, it is believed that the width 2 posets, although it is easy to show, is the one that's closest to violating the conjecture. Well, this is pretty intuitive in some sense. So if you have higher width, then you just really feel like the balance constant can be close to 1/2. Right? But this heuristic is not true for fully commutative elements. Fully commutative elements correspond to width 2 posets. So let W be this thing with sufficiently higher weights. So recall that in our previous theorem, we showed that the balance constant for an interval below a fully commutative element is at least 1/3. So this is our previous result. But you can construct some other convex set whose balance constant is strictly smaller than 1/3. Well, okay, so this is some example that shows that this heuristics of sort of the worst thing is not true in general. All right, that's all I have. Thank you very much for listening.
Thank you.
Thank you, Yibo. Let's thank the speaker. Are there any questions for Yibo?
If I had one, when I was listening to you, you know, like you base your generalization for Coxeter group, you all based it on inversion. And so your analog of a convex set is now defined by the number of permutation that is squeezed in between by two sets with regard to their inversion. Is there, I don't know if you know about that, I kind of remember in the back of my mind that there is a notion of higher inversion. Instead of looking at only pair, you look at triple that satisfies certain relation and things like that.
Like higher Brucha order.
Yeah. So is there in that context an analog of those constant and what they would look like and what we can say about that?
So it's a very interesting question, and I have absolutely no idea. Yeah, so I haven't looked at the connection between higher Brucha order and just like the traditional poset setting.
Yeah. But just you know, like it's a curiosity at this point. Like we don't know, but it seems like if you can generalize in this way, you can even
maybe you get like 1/3 then. Sorry, 1/4. That'll be amazing.
Yes.
So question is, So intuitively, one would think that if you take, say, larger polytope, then you should be able to divide it more evenly. So you should get like a better bound than 1/4, something closer to 1/2.
Yeah.
Is it possible to kind of say, make it more strict? I don't know, say that if your sets are somehow large, then you should be able to divide it better than, get better bound than 1/3.
Well, I mean, maybe being large is not the consideration because you can take something like a product and then this concept will be preserved.
Yeah, right. So that's like, yeah, question is there some kind of sensible way to define when these convex sets are large, so that for larger ones you should get more even subdivision?
I guess there can be ways of, you can probably make some argument of saying when you satisfy this, then you may just be able to get 1/2. But I think in general, in terms of poset, even this is a very, very hard question.
There's a question by Galen. Do you want to ask it, Galen, or do you want me to just read it?
I can ask it. So I was curious, around slide 31-ish, you gave a proof that involved volume, like a ratio of 2 volumes. And I was just curious, sometimes with hyperplane arrangement things, you can replace volume with another valuation, and either you get the same theorem back or you get something similar. I was curious what happens if you replace volume with a different valuation in this case.
That's a very good question. So I think the way of people improving the previous bounds uses something like that, use like Alexandro ventral inequality. I think we tried to, we definitely try some other version and see if other things can generalize, but some things are really type A, in lots of the proofs.
So by the way, you said like in the end you had this little twist for type B.
Yeah.
Can you say that you used a different valuation, or it's
more of a different polytope?
Different polytope. It's not different valuation, but generally different polytope.
So I have a question too, if that's okay.
Yeah.
So when you're defining these, the constants, the bounds constants for Coxeter groups, so there's a nice way to generalize this into, from what I see, I think there's a nice way to generalize this into like hyperplane arrangements or oriented matroids, using either the positive regions or the tope poset instead of the inversion sets. Have you guys looked into generalizing in that way, where you get a more larger family of objects to study, or is it mainly just Coxeter groups you looked at?
We've only looked at Coxeter groups, but it's 100% valid question to ask this question for hyperplane arrangement. I think I really remember some people emailing us about whether they can work like that, and we said go ahead. And maybe there are a few people working on this. I'm not exactly sure, but it really makes sense for hyperplane arrangement.
I remember either the few with Christian, we kind of discussed some point, and you described in this work, this question about other hyperplane arrangements appeared, and conclusion was that this 1/3 bound is not true in general for hyperplane arrangements.
Yeah, it's not true. It's I mean the simplest example in type A2. Well, you can have this convex region. Can you see? And then no matter how you cut it, it's going to be 1/4. This is affine type A2.
All right, so you kind of get problems with. Okay.
It's not going to be true, but I'm sure there will be interesting results.
That works. Are there any other questions? If not, let's thank the speaker again. And then so next week we have Alex McDonough, who will be talking about a higher dimensional sand pile map. So hopefully we'll see you all there. Thank you for joining.